You already know that ores can be concentrated by using any of the four methods: hydraulic washing, magnetic separation, froth flotation, and leaching. Now, let's see how crude metal can be extracted from its concentrated ore. The concentrated ore must be converted into an oxide, which is more suitable for reduction. For example, if we want to obtain crude copper from concentrated copper ore, we should first convert the concentrated copper ore into copper oxide, and then reduce copper oxide to obtain crude copper. Thus, the isolation or extraction of a metal from concentrated ore involves two major steps: converting ore into its metal oxide, reducing the metal oxide into the metal. Let's look at each step. Concentrated ore can be converted into its metal oxide either by calcination or by roasting. Let's see how these methods work. Calcination is the process of converting an ore into its oxide by heating it strongly below its melting point in the presence of a limited supply of air. It is usually carried out in a reverberatory furnace, as shown here. This method is commonly used to convert carbonate ores, such as calamine and dolomite, into their oxides. Also, the hydrated ores lose water of crystallization during calcination. When calamine, that is, zinc carbonate, is subjected to calcination, zinc oxide is formed and carbon dioxide is liberated. Similarly, when dolomite, a double salt of calcium carbonate and magnesium carbonate, is calcined, it gives calcium oxide, magnesium oxide, and carbon dioxide gas. On the other hand, when hematite is calcined, it loses its water of crystallization, as shown here. The other method for converting an ore into its metal oxide is roasting. Roasting is the process of heating an ore in a furnace with a regular supply of excess air at a temperature below the melting point of the metal. This process is commonly employed for sulfide ores. For example, sphalerite or zinc sulfide is heated at about 850 degrees centigrade to give zinc oxide and sulfur dioxide. Lead sulfide is roasted at about 600 degrees centigrade to give lead oxide and sulfur dioxide. When sulfide ores of copper, like copper pyrites, is subjected to roasting, copper is produced in the form of copper matte, which contains copper sulfide and iron sulfide. The iron oxide present as an impurity in the form of gangue is removed by adding flux silica. Iron oxide reacts with silica and slags off as iron silicate. Note that the flux added during the metallurgical process combines with gangue to form slag. The slag can be separated more easily than gangue. Roasting or calcination converts an ore into metal oxide and makes it porous. The metal oxide is porous because the volatile impurities are expelled and the moisture is removed during roasting or calcination. Now, the metal oxide is suitable for reduction. The metal oxide is reduced to metal by using a suitable reducing agent. The choice of the reducing agent depends on the reactivity series of the metal. When carbon is used as the reducing agent, it combines with the oxygen of the metal oxide to give metal and carbon monoxide or carbon dioxide. For example, carbon is used to reduce zinc oxide to metallic zinc. In this reaction, carbon monoxide is released. Generally, heating is required for a metal oxide to be reduced to its metal. The temperature at which a metal oxide will get reduced can be predicted based on studies that come under a branch of metallurgy called pyrometallurgy. On the other hand, thermodynamics helps us choose a suitable reducing agent for the reduction of metal oxide.